Hi everyone, welcome to my channel SciZap, and those of you for the returning viewers, welcome back. So today I wanted to start a new series in discussing the basics of system design and what they are before we move on into examples. So I will dedicate each video into discussing, for example, characteristics of a distributed system, load balancing, caching, etc. So before I begin today's video, I wanted to request that you like, subscribe, and share my video so that I can continue making more. And it really does make me feel a lot better if you leave a comment as well. So today we will talk about some of the system design basics, such as and some of the concepts that you should be familiar with. And this will help you prep for any fan company interviews, or even if you're trying to learn what a distributed system is and the considerations and the trade-offs to be made, this would be a great series for you. So the three considerations that I always think about before designing any distributed systems are: what are the different architectural pieces that can be used? Second, how do these pieces fit together with each other? Third, how can we best utilize these pieces, and what are the right trade-offs? So investing in scaling before it is needed is generally not a smart business proposition, but some forethought into the design can save valuable time and resources, especially costs, in the future. So in this video, I will try to define some of the core building blocks of a scalable system. Familiarize yourself with these concepts. It will help you understand distributed concepts better. For example, consistent hashing, cap theorem, load balancing, caching in general, data partitioning, indexes, proxies, queues, replication, and when to choose between a SQL versus a NoSQL. So now let's start by discussing scalability. Scalability is the ability of a system, process, or a network to grow, manage, increase demand. So any distributed system that can continuously evolve in order to support the growing amount of work is considered to be scalable. A system may have scale because of many reasons, like increased data volume or increased amount of work. For example, the number of transactions have increased. A scalable system would like to achieve this scaling without performance loss. So generally, the performance of a system, although designed to be scalable, declines as the system grows due to size and the management or environmental costs. For instance, network speed may become slower because machines tend to be further apart from each other. Or more generally, some tasks may not be distributed either because of their inherent atomic nature or because of some flaw in the system design. So at some point, such tasks would limit the speed up obtained by distribution, and a scalable architecture avoids this situation and attempts to balance the load on all of the participating nodes evenly. There are two types of scaling available. There's horizontal scaling and there's vertical scaling. So horizontal scaling means that you scale by adding more servers into your pool of resources, whereas vertical scaling means that you scale by adding more power, CPU, RAM, storage, to the existing server. So with horizontal scaling, it is often easier to scale dynamically by adding more machines into the existing pool. Vertical scaling is usually limited to the capacity of a single server, and scaling beyond that capacity often involves downtime and comes with an upper limit. So some good examples of horizontal scaling are Cassandra and MongoDB, and I want to discuss these at length and dedicate separate videos to them, as they both provide an easy way to scale horizontally by adding more machines to meet growing needs. Similarly, a good example of vertical scaling is MySQL. It allows for an easy way to scale vertically by switching from smaller to bigger machines, but it does come with a downtime. So think of vertical scaling as adding more machines, horizontal scaling is adding more servers, and you horizontally scale. The next concept is reliability. So by definition, reliability is the probability a system will fail in a given period. So in simple terms, a distributed system is considered reliable if it keeps delivering its services even when one or more of its components or software or hardware components fail. So reliability represents one of the main characteristics of the distributed system, since in such systems, any failing machine can always be replaced by another healthy one, ensuring that the task the user has started is completed. So take, for example, a large electronic commerce store or e-commerce store like Amazon, where one of the primary requirement is that any user transaction should never be canceled due to a failure of the machine that is running the transaction. So for instance, if a user has added an item to their shopping cart, the system is expected not to lose it. And a reliable distributed system achieves this through redundancy of both software components and data. So if the server carrying the user's shopping cart fails, another server has the exact replica of the shopping cart and it should be able to replace it. So redundancy has a cost and reliable system has to pay that in order to achieve resilience for services by eliminating every single point of failure. So the next concept is availability. So by definition, availability is the time a system remains operational to perform its required function in a specific period. It is a simple measure of the percentage of time that a system, service, or a machine remains operational under normal conditions. So an aircraft that can be flown for many hours a month without downtime can be said to have high availability. Availability takes into account maintainability, repair time, spares availability, and other logistics considerations. So if an aircraft is down for maintenance, it is considered not available during that time. So reliability is availability over time, considering the full range of possible real-world conditions and failures that can occur. So if an aircraft that can make it through any possible weather safety is more reliable than one that has vulnerabilities to possible conditions. So now let's think about availability versus reliability. So if a system is reliable, it is of course available. However, if a system is available, it is not necessarily reliable. In other words, high reliability contributes to high availability, but it is possible to achieve high availability even with an unreliable product by minimizing the repair time and ensuring that spares are always available when they're needed. So think of it this way. Availability is now, whereas reliability is now over a period of time and all the considerations that go with it. So now let's look at an example of an online retail store that has 99.99% availability for the first 2 years after its launch. However, the system was launched without any information security testing. So the customers are happy with the system, but they don't realize that this isn't very reliable as it is vulnerable to many likely security risks. So in the third year, the system experiences a series of information security incidents that suddenly result in extremely low availability for extended periods of time. This results in reputational and financial damage for the customers. Now, let's look at the concept of efficiency. To understand how to measure the efficiency of a distributed system, let's assume that we have an operation that runs in a distributed manner and delivers a set number of items as a result. So two standard measures of efficiency are the response time, known as latency, that denotes a delay to obtain the first item, and throughput or bandwidth, which denotes a number of items delivered in a given time unit. For example, in seconds or minutes. The two measures correspond to the following unit cost. So the number of messages globally sent by the nodes of system regardless of the message size, and the size of the message representing the volume of the data exchanges. So the complexity of operations supported by distributed data structures, searching for a specific key in a distributed index, can be characterized as a function of one of these unit costs. So generally speaking, the analysis of a distributed structure in terms of number of messages is oversimplistic. It ignores the impact of many aspects, including the network topology, the network load and its variations, the possible heterogeneity of the software and the hardware components involved in data processing and routing, etc. However, it is quite difficult to develop a precise cost model that would accurately take into account all of these performance factors. So we have to live with some kind of rough yet robust estimates of how systems behave. The next and last concept for this video would be serviceability and manageability. So another important consideration while designing a distributed system is how easy it is to operate and maintain. So serviceability or manageability is the simplicity, the speed with which a system can be repaired or maintained. If the time to fix a failed system increases, then the availability will decrease. So things to consider for manageability are the ease of diagnosing and understanding problems when they occur, ease of making updates or modifications, and how simple the system is to operate in general. For example, does it routinely operate without failure or exceptions? So the way to mitigate this is early detection of faults. It can decrease the downtime in a distributed system. For example, some enterprise systems can automatically call a service center without human intervention when the service experiences a system fault. So to conclude, we have covered scalability, under which you have vertical versus horizontal scaling. Then you have reliability, availability, efficiency, serviceability versus manageability. So for scalability, you have vertical or horizontal scaling. Vertical scaling is adding more RAM capacity. Horizontal scaling is adding more servers, usually virtual. Reliability is availability over a period of time so that it's fault tolerant over a longer period. Availability is making sure that the system performs well now and you have some kind of mechanism so that the user can complete any transaction, for example. So if a system is reliable, it is available, but it's not the other way around. If a system is available, it is not necessarily reliable because we don't know how it will function over time. Efficiency, you can measure it in two ways. There is latency, how quickly the computer or the application responds back in time the first time you use it, or throughput, which denotes the number of items delivered in a given unit of time. Then you have serviceability versus manageability, which again affects availability. So for now, I will conclude this, and please stay tuned for my next video and I'll discuss other important concepts. Bye. Oh, don't forget to like, subscribe, and share my videos. Bye.